All right, so tonight is lesson 3 of hazardous materials operations. We're going to talk about chemical properties and health effects of hazardous materials. We're going to start out with the chemical properties. So the 3 states of matter that we normally deal with: solid. Keep in mind that we need to know some details about each one of these states of matter. So a solid has both a specific shape, even without a container, and volume. Those are fixed. With a liquid, it's a fluid that has no independent shape, but does have a specific volume. Keep in mind that liquids will take the shape of the container, and also they flow according to the laws of gravity. A gas is a fluid that has neither an independent shape nor volume and tends to expand indefinitely. So a gas will take the shape of its container and the volume of its container. If you change that container, it will change the shape of the gas and its volume. Compared to a liquid, if you change the container, it will change its shape, but will not change its volume. So how does temperature affect the state of matter? So as we increase the temperature of a material, it will change its state of matter. It will change its phase. It will go from a solid and then to a liquid into a gas as we raise the temperature. There are other physical properties that also change with temperature in relationship to volume and pressure as well. We also need to know some definitions of the chemical properties. So flash point is the minimum temperature at which a liquid or volatile solid gives off sufficient vapors to form an ignitable mixture with air near its surface. This is not self-sustained. So a flash point is a temperature. Anytime we see the word point, we need to think of a temperature. When we see flash, we should also think of not self-sustained. Next, we have fire point. Again, we see the word point. That means it's a temperature. Fire point is the temperature at which enough vapors are given off to support continuous burning. So this is a temperature greater than the flash point temperature, which is self-sustained. So the fire point is self-sustained. As long as we maintain that temperature of or above, we will maintain fire. Auto ignition temperature / point can be one of the two. We see both of those terminologies. Again, it's a temperature. It's the minimum temperature at which the fuel and air must be heated to initiate self-sustained combustion without initiation from an independent ignition source. So this is, we apply heat to a substance, and when it reaches this temperature, it will combust. With the fire point, so the auto ignition temperature is somewhere between, it is somewhere higher than the fire point. The fire point requires an independent ignition source. Fire point requires an independent ignition source. The auto ignition temperature is greater than that and does not require an independent ignition source. The next term is flammable, explosive, or combustible range. So when we talk about a range, we're talking about a percentage of the gas or vapor concentration in air that will burn or explode if ignited. So this is independent of temperature. This is not a temperature. This is a percentage of gas concentration. It can be measured in parts per billion, parts per million, or percent of air. So there's the details of this range. So we talk about there's a lower range and an upper range, and we call those limits. The lower explosive or lower flammable limit, depending on the material, is the lowest concentration, usually in a percent, that will produce a flash of fire when an ignition source is present. The lowest concentration. So we talk about a lower explosive limit, or LEL. We're talking about a concentration. When we talk about the UEL, or the upper explosive limit or upper flammable limit, this is the highest concentration that will produce a flash of fire when an ignition source is present. Keep in mind, some materials, like ethylene oxide, have no upper limit. They will burn at 100%. Ethylene oxide provides its own oxygen to support combustion. So what does this mean? There are most chemicals where there is a lower limit to which they will explode, that they will support combustion. So let's, for example, we have a chemical that has a lower explosive limit of 5%. If we have a concentration less than that, say 2%, we are not in danger of that gas combusting. That's what that means. So if we're below that lower concentration, that lower explosive limit, we are not in danger of an explosion. Say this chemical has an upper explosive limit of 25%. If we add enough of this gas to air in a confined space, because if it wasn't confined, it would just dissipate. We have enough concentration, and it's greater than 25% in this example, then it will also not combust. Keep in mind that if anything disturbs that concentration and brings the concentration within that flammable range, in this case between 5 and 25%, then we are in a combustible atmosphere. Vapor pressure. This is the pressure exerted by a saturated vapor above its own liquid in a closed container. Okay, so this is usually deals with things that are either a liquid or a gas in our normal environmental temperatures and pressures. This is usually expressed in multiple units. It can be in pounds per square inch, PSI. It can be in kilopascals, kPa, millimeters of mercury, or atmospheres. Temperature relates to vapor pressure, to a substance's vapor pressure. The higher a substance's temperature, the higher the vapor pressure. This is pretty evident even with water. If we had water on a surface and we heated, say we put water in, we had two pans, put the same amount of water in the two identical pans. We heat one pan and we let one pan remain at room temperature. We have the same amount of water. When we heat the water, its vapor pressure in that pan will rise. And therefore, more of the water will convert to a vapor. So think of vapor pressure as a liquid's willingness or a substance's willingness to be a gas. Things with higher vapor pressure want to be a gas. Things that are gas at our normal temperatures and pressures, those chemicals have very high vapor pressures. So you can just, not knowing anything else about the chemical, you can look up its vapor pressure. And if it's several times normal atmospheric pressure, then it's probably going to be a gas. That's how one way we can figure out what state of matter a material we can expect it to be in. The lower a substance's boiling point, the higher its vapor pressure. This is kind of in that same idea. That way, if you know that a substance's boiling point is really low, then you know it's wanting to be a gas. Because if it was high, then it would stay a liquid longer, because the transition from a liquid to a gas we call boiling. Its boiling point. The temperature at which it transitions is its boiling point. So what is atmospheric pressure? It's the force exerted by the weight of the atmosphere at the Earth's surface. So air is matter, made out of matter, therefore it has mass, therefore it has weight. Here are some standard atmospheric pressures. Now these are at sea level, at a specific temperature. We live at about 450, 500 feet above sea level, so our atmospheric pressure is a little bit less than standard. Can't tell you what it is exactly, and it does fluctuate. But take these as an average, or at least a line to which you can compare vapor pressures to. These are just some numbers. I have, over the years, just remembered these. So when I see a vapor pressure listed, I can tell you how much that chemical wants to be a gas. The closer it is to the standard atmospheric pressure will press down on that liquid and keep it from converting to a vapor or a gas. So 14.7 pounds per square inch, 760 millimeters of mercury, 29.92 inches of mercury, or 1013 kilopascals. Because different chemicals the vapor pressures are listed in different units, so it's just a good idea to kind of have an idea of what the standard atmospheric pressure is. That way you can get an idea of what that material is going to do. Boiling point, we talked about, is the temperature at which the vapor pressure of a liquid is equal to or greater than atmospheric pressure. It's expressed in degrees of Fahrenheit or Celsius at sea level and air pressure, at sea level air pressure. Melting point is the temperature at which a solid substance changes to a liquid state at normal atmospheric pressure. And then freezing point is the temperature at which a liquid becomes a solid at normal atmospheric pressure. So what's the difference between melting point and freezing point? Most things are going to be the same. It just depends on whether you're adding heat to that chemical or removing heat from the chemical. Sublimate, to change directly from a solid to a gas without entering a liquid state in between. The most common example is carbon dioxide. We can take frozen carbon dioxide, solid carbon dioxide, set it out on a counter, and it will convert. It will not melt into liquid carbon dioxide. It will convert directly to gaseous carbon dioxide. Bleve, B-L-E-V-E, bleve, boiling liquid expanding vapor explosion. Now, we talked about how when we increase the temperature of material, that also increases its vapor pressure. If a material is inside an enclosed container, that pressure has nowhere to go. And if that pressure exceeds the capability of that container to withstand that pressure, then that container will open. So it occurs when a liquid within a container is heated, causing the material inside to boil or vaporize beyond the vessel's ability to relieve the excess pressure. So we have, these usually happens in high pressure containers, so the ones with the round ends. There's a liquid inside that has a high vapor pressure. It's usually flammable. Heat is applied, usually in the form of external fire, flames impinging on the container. It boils the liquid inside because it has a low boiling point, therefore creates a vapor which has a higher pressure until that container can no longer withstand the pressure. It violently ruptures, and there is a immediate release of that energy, usually in the form of an explosion. And since it's a flammable liquid and gas, and there's fire already involved, it usually involves fire as well. Bad news. Vapor density. Don't confuse vapor pressure with vapor density. Vapor density is the weight of a given volume of pure vapor or gas compared to the weight of an equal volume of dry air at the same temperature and volume. So all things being equal, volume, temperature, then we compare a chemical, gaseous chemical, to air because we're surrounded by air. So we need to know what this gas is going to do. So there's three things it can do. It can just sit and not go anywhere in its normal altitude. If the vapor density is less than the number 1, so anything less than 1, the vapor will rise. Air, we give there's no unit to it. Air just has a vapor density of 1, because remember, this is a comparison. So we can set any point we want. Air, we give a number of 1. So anything less than a 1, the vapor will rise. If it has a vapor density greater than 1, it will sink. So for example, methane has a vapor density less than 1. It will rise. So if there's a methane leak outdoors and it's free to vent to the air, that's great. It's just going to rise and rise and rise and rise and go away. The danger with that comes in if it gets trapped somewhere, but also the area immediately surrounding the release, the opening, could have concentrations within its flammable range. So we still need to be careful around it, but it's a better situation than with, for example, propane, which has a vapor density of greater than 1. It's going to sink. It's going to find low spots and hang out there. It's going to collect in low spots. So if you had a pipe in a ditch, and it's leaking into that ditch, it's going to stay in that ditch and not rise and dissipate. A little bit more dangerous situation because we're on the ground closer to that ditch than up in the air where the methane's going. Solubility. So solubility is the percentage of a solid by weight that will dissolve in water at ambient temperature. So it's usually a solid, also a liquid, can be described as being soluble. So this is some substances are non-water soluble if they remain separate when combined with water. Okay. Solids, like I said, give a percentage. So if something's 100% soluble in water, it means it will completely disappear. There's usually a point at which the water will no longer hold that solid in solution. So it would not dissolve beyond that point. Some materials have a less than 100% solubility, and it just kind of gives you an idea of what it's going to do when it encounters water. Miscibility is the degree or readiness with which two or more gases or liquids are able to mix with or dissolve into each other in any proportion. So that means that it doesn't matter how much you have of each component of the mixture, they will either mix or not. So we use the word miscible, liquids that dissolve into each other. So water and ethanol are miscible. Water and gasoline are immiscible. They do not readily dissolve into each other. Okay. So liquids that dissolve into each other, we can dilute. Things that are immiscible, we cannot. They remain separated. So when things are immiscible, we need to know, are they going to sit on top of the water, or are they going to sink to the bottom of the water? We use the term specific gravity to know which one of those is going to happen. So specific gravity is the ratio of the density of a liquid to the density of water at standard conditions of pressure and temperature. We give water, just like with air and vapor density, we give water its specific gravity of 1. If the specific gravity of the chemical we're comparing it to is less than 1, it'll float. If the specific gravity of the immiscible liquid or chemical is greater than 1, then it will sink. Toxicities, the ability of a material to harm, destroy, poison, kill, or otherwise damage body tissue. Toxicity. Corrosivity, the ability of a material to damage skin tissue and or metal. Instability, the ease in which a chemical may undergo a rapid and sometimes violent chemical change. We refer to the unstable compounds. They react quickly with little or no outside energy in given situations. Reactivity, the ability of a chemical to react with other chemicals. There's two types of reactivity, two types of reactions that we're going to talk about. We have exothermic reactions, which are those reactions which release heat to their surroundings. An example would be heat packs, hand warmer heat packs, or heat packs on an ambulance. Endothermic reactions, those reactions which absorb heat from their surroundings, such as cold packs, chemically activated cold packs. Substances referred to as reactive commonly react violently with air, water, heat, light, each other, or other materials. So reactive materials are unstable. When we're talking about reactivity, there's a reactivity triangle. It explains the basic components of many chemical reactions. So in order to have a chemical reaction, you have to have, in our sense, you have to have an oxidizing agent, a reducing agent, also known as the fuel, an activation energy source, often heat. Taking a look at this, it looks very similar to the fire triangle. The fire triangle is a reaction. It's an exothermic reaction. It has the same components required to occur as any other reaction. Remove any one of these and the reaction stops. When it comes to a chemical reaction, sometimes, other than fire, sometimes it's a little difficult. Compatibility, the ability of two materials to remain in contact without a reaction. Sometimes you can mix chemicals together, and nothing will happen. However, if two commodities react, they are identified as incompatible. If that happens, there's a chance that the reaction may present a hazard to responders. For example, there are some chemicals that are incompatible with organic material. So what does that mean? If we try to use soil or sand to build a dike to confine a material, and that material is reactive with water or organics, soil is full, but full of organics, and sand probably has water in it, and probably some organics as well. We wouldn't want to do that. What does organic mean? It means it has hydrocarbons in its structure. When we talk about organics, usually we're talking about things that formerly were alive, plant material, animal material. Polymerization. It's a chemical reaction in which a catalyst causes simple molecules to combine to form long chain molecules. So if that happens slowly, no big deal. When it's danger to us, it happens rapidly, usually involves high pressures and high temperatures. That's when it's bad. Inhibitors are materials that are added to products they're added to products that normally are easy to polymerize. They're added in order to control or prevent an undesired reaction. So you have a chemical that easily polymerizes in case it's subjected to heat or light or shock, physical shock. They'll add an inhibitor to reduce that from happening. All right. So exposure and contamination. It is critical that you understand the difference between exposure and contamination. So an exposure occurs when a person has actual contact with an agent in any physical form, whether that agent is a solid, liquid, gas, or radioactive particle, regardless of your protection. I'm sorry, or not radiation particle, any type of radiation, whether it's a particle or a ray. So this means the substance has touched you. It has the potential of affecting you. Okay? It has the potential to affect you. It has touched your skin, your eyes, you breathed it in, you swallowed it, it's been injected into you, or you have been in the presence of radioactive rays. Okay, there is internal exposure and there's external exposure. Internal is inside your body, external is outside your body. That's exposure. You've had actual contact with whatever it is. Contamination is when matter is physically left on an object or person. Okay? Primary contamination means you got it in direct contact with the substance, such as working in the material in the hot zone. So any victim who has, whatever at the time of the release or even after the release, anytime after the release, anybody that touches the material where the release is occurring receives primary contamination. Secondary contamination is contamination through contact with tools, clothing, or personnel which have been previously contaminated and thus carry the contaminant out of the hot zone. Okay? Secondary contamination means the material was brought out of the isolation or the hot zone and it was transferred to something else. So you would receive secondary contamination in the warm zone. We haven't talked about that yet, but we will. During the decontamination process, or in the cold zone, because something did not get decontaminated appropriately or completely. That's where you would get secondary contamination. Keep in mind, part of the difference between contamination and exposure is contamination may be spread, exposure cannot. For example, if you're sitting in a room and the light is on and a light is on in the room, you are exposed to the light. If there were negative or positive effects of that light, then you would experience them. However, if you leave the room, you are not contaminated with that light. If you leave the room, you don't take it with you. You can't spread it to someone else. Okay? If you are wearing proper PPE in the proper way, and you get the hazardous material on your chemical protective suit, you are contaminated, but you are not exposed. You are contaminated, but you are not exposed. As long as that chemical protective suit is the appropriate suit for that chemical. Hazard. This is the degree of risk associated with an exposure. How much the hazardous material is going to harm you, or what effect that hazardous material is going to have on you. Sorry, it is the degree of risk. You can have a low hazard, a moderate hazard, or a high hazard. How does a material get in you? There are 4 routes of entry. They are inhalation, which is through the lungs, you breathe it in, ingestion through the mouth and the gastrointestinal system, absorption means you got it on your skin, it goes through your skin barrier, injection, it goes past the skin via punctures, such as needles or shrapnel. So inhalation, ingestion, absorption, injection. Those are the 4 routes of entry. That's how a hazardous material will get in you. So how does a hazardous material harm you once, or hurt you, affect you once you've been exposed? Well, there are 7 types of harm. Here's the easy way or easier way to remember them. The mnemonic trace them P. We're going to talk about each one: thermal, radiological, asphyxiate, chemical, etiological, mechanical, and psychological. No particular order. All right, so what is thermal harm? Thermal harm is excessive cold or heat. Both can cause permanent tissue damage, induce shock, or cause death. Remember, thermal is hot or cold. Radiological. These are high energy waves and particles emitted from radioactive materials. There are 2 general types of radiation. There's non-ionizing radiation. This does not cause chemical changes to the objects irradiated. It may, however, cause damage to the heating due to heating of the material. So radar, heat radiation, microwave radiation, your portable radio used in the fire department, the radio used in the radio transmitter that sends radio signals to your vehicle. Those are types of non-ionizing radiation. Wi-Fi, cell phone, those are non-ionizing radiation. They are frequencies lower than visible light. Visible light is radiation. It's non-ionizing. Ionizing radiation, which is above in the frequency spectrum of visible light, it comes from decomposing nuclei and is capable of chemically altering the object being irradiated, the object receiving the radiation. Ionizing radiation. That's the bad stuff. Radiation injuries. So there's irradiation injuries and there are contamination injuries. So irradiation injuries, these are people or objects which have been irradiated by a source of ionizing radiation, are not a source of great danger to responders. This is similar to a person receiving a sunburn. Contamination injuries. People or objects which have been contaminated with radioactive material particles, either internally or externally. These pose a risk to responders. The persons are now sources themselves. So irradiation injuries means they received a radiation dose. They were exposed to radiation, but they're not contaminated with radioactive material. So for example, when you go get a chest x-ray, an x-ray is a type of ionizing radiation, similar to gamma radiation, which we're going to talk about here in a second. People who have been exposed to gamma radiation don't take that gamma radiation with them. It does not make them radioactive. Okay? Those people are not necessarily a danger to responders. People who have, or things, objects who have been contaminated with radioactive particles or radioactive materials are a danger to first responders. Okay? Now, they're not radioactive, but they now have radioactive materials on them. So what are the exposure effects of radiation? So some effects may not be seen for days to a week after the exposure. High doses or moderate to high doses, symptoms include a loss of hair, bleeding from the gums, nausea, vomiting, immune deficiency, bruising, etc. Radiation sickness is due to the exposure of high levels of radiation. It takes days for all symptoms to appear, may take up to 8 weeks to recover. You're just sick. Radiation injury, local injuries usually confined to areas most directly to the source. Hand burns are common because people pick things up. and they get the radiation burn. Radiation poisoning, this means you got the radioactive material inside you, and you've now internalized that source. So types of radiation that we're going to talk about alpha particles, beta particles, gamma rays, X-rays, and neutrons. So an alpha particle, they're positively charged particles that lose energy rapidly and do not penetrate very far. They are literally a helium nucleus, 2 protons, 2 neutrons. Relatively, they are heavy, relatively in atomic speaking, they are relatively heavy. They are commonly emitted in the radioactive decay of the heaviest radioactive elements, such as uranium and radium, as well as by some man-made elements. There's very little naturally occurring radioactive materials. Very few. Most of the radioactive elements and materials that we know of were created in a nuclear reactor. The alpha particles, they're usually completely blocked by the dead outer layer of the human skin. They're blocked by your clothes, a sheet of paper. Doesn't take much to block alpha particles. If they're outside the body, they're not a hazard. Okay? Beta particles. These are fast-moving, positively or negatively charged electrons. So they can move fast because electrons, atomically speaking, are very lightweight. They're emitted from man-made and natural sources such as tritium, carbon-14, and strontium-90. These are more penetrating than alpha particles over equally traveled distances. So alpha particles don't travel very far, but so if you got to the outer limit of alpha particle, beta particles would be more penetrating at that distance. Beta particles take a little bit more of substance to block. You would need a sheet of aluminum to block beta particles. So far, beta particles, alpha particles, they can be blocked by your fire truck. So as long as you're on the opposite side of the fire truck, you're good to go. Your bunker gear will not protect you from beta particles. It will protect you from alpha particles. Beta particles are capable of penetrating the skin, causing radiation damage, but are more hazardous when inhaled or ingested. Okay. So with alpha and beta, you do not want it inside of you. So those routes of exposure, don't let it get injected, don't eat it, and don't breathe it in. We talked about how you can stop it. Your fire truck or a car. All right, so now we're moving up in increasing energy. Gamma rays are high energy photons. They are the same thing as visible light, just at higher energies and higher frequencies. They often accompany alpha or beta particle emissions, which means you could have a substance that is an alpha and gamma emitter or a beta and gamma emitter. We know how to protect ourselves from the alpha and beta. The gamma takes a little bit more effort. Since they are photons, they have no charge, but are very penetrating, easily passing through the human body and absorbed by tissue. To an extent. Gamma rays are very small, even smaller than the electrons. They, for the most part, when a gamma ray encounters an atom, relatively speaking, again, an atom is mostly space. So most of the time, that gamma ray just passes right through the atom. Your body's made of atoms, so most of the time, the gamma rays are going to pass through your body without making any change. Every once in a while, it will hit that your matter and could change some of its components, such as your DNA, which is bad. So how we stop it? They require several feet of concrete or a few inches or millimeters of lead to stop the more energetic gamma rays. They can easily penetrate standard firefighting clothing, which provides no protection from gamma rays. X-rays, high energy photons, just like the gamma. They have essentially the same properties. They originate outside the nucleus, while gamma rays originate inside the nucleus. They are the single largest source of man-made radiation exposure because we get X-rays all the time. Remember, it's exposure. You're not contaminated. So thinking about exposure and contamination, think about which that we've talked about so far: alpha particles, beta particles, gamma rays, X-rays. Which of those can you be exposed to? All of them. Which ones of those can you be contaminated with? Alpha and beta. They are particles. You can be contaminated with those particles. However, you can also be contaminated with gamma emitting materials. But you're not the source. You have not been made radioactive. X-rays are generally lower in energy and thus less penetrating. The gamma rays, they could be stopped with a few millimeters of lead. Neutrons are ultra high energy particles that have a physical mass like alpha radiation, but no electrical charge. They are highly penetrating. They are produced along with gamma radiation from fission reactions. So neutron radiation is produced in nuclear reactors. They are not commonly used in commercial industrial operations, usually only encountered in research laboratories. They can cause the release of secondary radiation and thus are a health hazard. Should never encounter neutron radiation. So radiation exposure occurs when radioactive particles or rays enter the body through one or more routes of entry. We talked about inhalation, ingestion, absorption, and penetration. Radiation contamination occurs when radioactive materials deposited on surfaces, skin, clothing, or any place where it's not desired. You can have it outside, externally, internally, or environmentally. All right, so radiation protection strategies. Now, most of the time, these three steps or three methods are used in relation to radiation. However, you can use these three protective methods or characteristics to protect yourself from any hazard, whether it be radiation, a chemical hazard, or a hazardous relationship. And those three things are time, distance, and shielding. Pretty simple. Don't spend a lot of time with the things that are hazardous to us. Limit your time. Distance yourself physically. Don't hang out next to that dangerous chemical or that unhealthy person. And then shielding. We talked about how a piece of paper will block, or even your clothing will block alpha particles. You need several feet of concrete or water or lead to block gamma rays. You can also put up those emotional walls to shield yourself from those hazardous people. All right, so radiation protection strategies. Wearing personal protective equipment, including SCBA, generally protects emergency response personnel from external and internal contaminants. However, it does not protect against exposure to gamma rays. So putting on PPE, so say your bunker gear and SCBA, that is shielding. Those things are shielding. They will, so what do you have? So if that's not going to protect you, you have distance and time. If you have to make a viable rescue, put on that bunker gear and SCBA, spend as little time as possible, and keep as far away from the source as possible to limit how much you're exposed. Continue with the types of harm. We've talked about thermal and radiation. Now we're going to talk about asphyxiants. So what do asphyxiants do? They affect the oxygenation of the body and generally lead to suffocation. There's two types of asphyxiants. There's simple asphyxiants. These are gases that displace the oxygen necessary for breathing. So these are gases that displace in the area that you're in. So if you're in a room and a gas is leaking and it pushes the oxygen out, that is a simple asphyxiant. Chemical asphyxiants, these are substances that prohibit the body from using oxygen. So they get into your body and prevent the oxygen that your blood's transporting around your body, prevent it from doing and going where it needs to go. Those are chemical asphyxiants. We talked about thermal, radiation, asphyxiants. Now we're to chemical harm. We got some subclasses of those. We have irritants. These are toxins that cause temporary but sometimes severe inflammation. So these would be things like pepper spray, mace, things like that. Convulsants, these are materials that cause convulsions, involuntary muscle contractions. Corrosives are acids and bases. Toxins are they target organs or systems. So toxins could be, if we go into that, well, I think we talked about that later. Mutagens, these are things that are capable of altering your genetic material. And teratogens, these are capable of causing developmental abnormalities in utero, which means they cross the placental barrier. So irritants, you can have upper respiratory irritants, you have lower respiratory irritants, terminal respiratory irritants. They cause irreversible tissue damage, and then there's also internal irritants. Acids, they destroy the tissue while often generating heat, causing chemical and thermal burns, irritation, or itching. The opposite of that is bases, also called alkalis or caustics. They destroy tissue while reacting with the fatty tissue in the process known as saponification. This literally turns the tissue to soap. These cause typically extensive damage is done prior to the victim even noticing the burn, since they're not initially painful. So they go right through the skin, they start affecting the fat, and you don't even know it. They also cause caustic burns tend to be deeper because they go right through the skin and attack the fat layer. All right, so when we're talking about corrosives, there is a measurement of corrosivity. It's called the pH scale. The pH of a corrosive will provide the responder with a relative measure of its corrosive abilities. So the scale goes from 1 to 14. 7 in the middle there is considered neutral. So it's neither an acid nor a base. Any number, any pH less than 7 is an acid. Any pH greater than 7 is a base. Keep in mind, each whole number change in pH, so from a 7 to an 8, reflects a strength change of 10 times. A 3 is 10 times stronger than pH of 4, or 100 times stronger than a pH of 5. Okay? It's not linear. It's not just doubled or whatever. It's logarithmic, which means it gets worse really fast. Normal body pH is 7.35 to 7.45. Just to give you an idea, that means our blood is normally slightly basic. When we start talking about toxins, poisons, and allergens, there are some terms to help us determine how toxic a material is. We'll start out with the lethal dose. This is the minimum amount of a solid or liquid that, when ingested, absorbed, or injected through the skin, will kill something. So this is the lethal dose. It's the minimum amount. The smaller that amount, usually measured in grams, the smaller that amount, the more toxic the material is. There's also a term called the median lethal dose. It's described as LD50. This is statistically derived single dose of a substance that can be expected to cause death in 50% of animals when administered by the oral route. So they figure out how scientists, researchers figure out how much of a material will kill 50% of the 50% of the subjects that they expose it to when ingested. Again, the smaller the number, the more toxic the material. The lethal dose low is the lowest administered dose of material capable of killing a specified test species. So below that, it doesn't kill anybody. Don't see that very often. Usually you see the LD50. For gases, we have the LC50, or the lethal concentration 50. It's the concentration of an inhaled material, gas, which causes 50% of a test population to die. Also, there's a lethal concentration low. This is the lowest concentration of a gas or vapor capable of killing. You can also see ID50 or ID10. This means the material incapacitates 50 or 10% of the population, tested population. I don't see that very often. Mostly see LD50 and LC50. So we know that some materials are okay to be exposed to up to a certain amount or up to a certain amount of time. So this is what these terms reference. So we have the threshold limit value time weighted average, or the TWA, usually just referred to as a time weighted average. This is the average concentration for a normal 8-hour workday and a 40-hour work week to which nearly all workers can be repeatedly exposed day after day without adverse effect. So time-weighted average is an 8-hour workday. So what does this mean? It means that the government has said that you can average this exposure for 8 hours. and be okay. So for example, carbon monoxide, that number is 50 parts per million. So the government has said you can average exposure to 50 parts per million. You can dip a little bit below that, a little bit above that, but average 50 parts per million over an 8-hour period, and you'll be okay. Next is the short-term exposure limit. This is the concentration to which workers can be exposed for short periods of time, and they won't be irritated or have chronic or irreversible tissue damage or narcosis. That means becoming unconscious to a sufficient degree. The value is typically usually for a 15-minute exposure. Okay, so I don't know what the short-term exposure limit for carbon monoxide. Let's say it's 200. Government says you can be exposed to carbon monoxide at a concentration of 200 parts per million for up to 15 minutes, but not more than 4 times a day, and separated by at least an hour. Again, I just made that 200 up for carbon monoxide. I just don't know what it is. But it's going to be higher than the short term. I'm sorry, the time weighted average. So time weighted average is 8 hours. Short term exposure limit is 15. Then we have the threshold limit value ceiling. This is the concentration which never should be exceeded. Ceiling, never exceeded. Should never be expected to work in that concentration or higher. There's also permissible exposure limits. This is the level to which OSHA will allow workers to be exposed and is similar in application to the time-weighted average. There's also recommended exposure limits. This is the concentration that limits up to a 10-hour workday. And there's also IDLH. You've probably heard this before. It means immediately dangerous to life and health. This is a concentration limit at which over a 30-minute exposure, the material is likely to cause death or delay permanent damage or prevent a worker or cause delayed permanent damage or prevent a worker from escaping a given contaminated environment. This is usually the level at which we put on PPE. Beyond the IDLH concentration, you need PPE, anything greater than that. Poison can harm or kill, inhibiting the body's normal biological activities. There's also target organ poisons. They attack certain tissues or organs of the body. It can also accumulate in these organs for over long or short periods of time, causing a range of damage from little to severe. For example, hepatotoxins or liver poisons are classic examples. Neurotoxins, these are materials which produce toxic effects on the central nervous system. We have 2 basic types of central nervous system. We have the central nervous system poisons. These are materials which disrupt or alter the nervous system. Chemicals such as organophosphates and chemical warfare agents are recognizable examples. Then there's also peripheral nervous system poisons. They damage the nerves which transmit information to and from the brain. Anesthetics, these are substances which cause lack of feeling. They may alter perception or give the appearance of being under the influence of alcohol, and in large doses act as narcotics. These compounds will often be target or organ poisons as well. Narcotics are substances which cause sleep. These may cause anesthetic effect and altered consciousness in low doses. Low doses may cause death or coma. These are examples of some other types of toxins, poisons, or allergens. We talked about hepatotoxins, nephrotoxins cause kidney damage, reproductive toxins, cutaneous harm, affects the skin, eye harm, Allergens are substances that cause allergic reactions. Carcinogens cause cancer. And sensitizers, they cause an allergic reaction after repeated exposure. Just an allergen, you can have an allergic reaction after one at the very initial exposure. Sensitizers takes a repeated exposure for you to cause an allergic reaction. So that finishes up chemical. Now we're going to move on. So we talked about thermal, radiation, asphyxiant, chemical, and now we're etiological. These are exposure to microorganisms or their toxins. Etiological means biological. Put that in your brain. Etiological means biological. It means the source is biological. So examples would be bacteria or viruses. Corona, anyone? We have an etiological hazardous material incident going on for almost a year now. Botulism, anthrax, plague, HIV, Ebola, all examples of etiological harm. Next is mechanical harm. This is direct contact with an object, such as being struck by a falling or flying object in the presence of an explosion. So remember we talked about that BLEVE, that boiling liquid expanding vapor explosion. That tank ruptures and explodes, and part of that tank hits you. You've just received mechanical harm. Psychological. As with any incident, the stress of dealing with severe trauma, destruction, death, or even with the slow pace of a hazardous material incident may place large amounts of stress on individuals and the responders as a whole. So just responding to a hazardous material incident can cause psychological harm, either to the initial victims or to the responders. So it's just another type of harm that hazardous materials causes. It's important to realize that chemicals are capable of producing more than a single type of harm at once. They have multiple hazards. So gasoline, it's a carcinogen and it's flammable. All right. Another example would be hydrofluoric acid. It's both poisonous and corrosive. A drop on your skin will kill you. It'll also eat through a metal container. There are immediate health hazards and there are delayed health hazards. So immediate health hazards means you're going to feel the effects almost immediately. There's delayed. Usually it takes a while. We talked about the radiation sickness or radiation injury. Could take days for those to appear. So what are the factors that affect harm? So the first thing is the concentration. So that's the amount of substance in a mixture or of a solute in a solvent. So a solute, for example, would be table salt, and the solvent would be water. So the concentration is how much of the bad stuff compared to either water or air. Okay. So for example, H2S, hydrogen sulfide. The ideal H concentration is 100 parts per million in air. In order to purify water with bleach, you need 0.013% of bleach in water. Depends on the concentration. Above that, it's dangerous. Either one of those, the concentration, parts per million, percent. There's always a comparison, an amount to another amount. Your exposure duration, how long were you exposed? We talked about that time component in time, distance, and shielding. This is that time component. You can have an acute exposure. This is a single exposure, often large concentration of short duration. That's acute. You have a chronic exposure. This is long-term repetitive exposure. So something that works with a hazardous chemical. Something that works with it 40 hours a week, 52 weeks a year, over 20 years, for example. You have chronic, long-term repetitive exposure. Also, you have the dose. This is the amount of the substance which enters the body. Often, the difference between a medicine and poison is the dose of the material. For example, Tylenol. At a certain dose, a certain amount, it's a medicine. You exceed that dose, and now it's a poison. So that's not a concentration, that is the actual amount of the material. The route of exposure, how it gets into your body, will affect the harm. For example, some chemicals may have very limited ability to penetrate the skin, but may cross the body's barrier in the lungs very easily. So, for example, mercury. You can put your hand in mercury and have no ill effects, but you breathe in mercury vapor, now you're going to have some problems. Dose response. So the dose response characteristics of a particular chemical will have an effect on the harm. Some chemicals harm in very small concentrations, while others will require large concentrations. Water, perfect example. In small concentrations, water, we require it. But we drink too much, or we try to breathe too much, and it will kill us. Personal variables also can be a factor. Family history, your fitness, your sex, your age, all can be a factor in how much harm is done by an exposure. Some signs and symptoms of the harm that hazardous materials can affect. Confusion, lightheadedness, anxiety, dizziness, blurred or double vision, changes in skin color or blushing, coughing, painful respiration, tingling or numbness of the extremities, loss of coordination, nausea, vomiting, abdominal cramping, diarrhea. These are just some examples. And looking at those signs and symptoms, many of those are very common signs and symptoms to non-hazardous materials illnesses. So that's the end of chemical properties and health. Our next class is Wednesday, February 10th, I believe. Yes, 10th. Right back here at 7:40.